First introduction. My name is Ba-asani. Question 1. Outline an algorithm for finding a minimum spanning tree, MST, in a distributed system. Follow up. In what real-world ML scenario would you use MSTs, e.g., sensor network feature selection? Answer. A minimum spanning tree, MST, can be constructed efficiently using algorithms designed for decentralized environments where nodes have limited knowledge of the entire network. MST is a graph theory algorithm that connects each node using wire, and each wire have different expensive. Main purpose of this MST is to connect one network to another and minimize the expensive of wire of each node. In real-world ML scenario we would use feature selection because feature selection identifies sensors with low redundancy and high coverage. Connected sensors and MST provide complementary, not duplicate, information. Removing high-weight edges splits the MST into clusters of similar sensors. Select one representative sensor per cluster. Question 2. Given a large stream of user interactions, design a data structure for O, log n, range some queries and updates, supporting both exact and approximate aggregation for downstream feature generators. Follow up. How would you parallelize updates for distributed feature stores? Answer. Data structure, exact, Fenwick tree, binary index tree, bit or segment tree. Fenwick, prefix some queries O, log n, point update O, log n, range sum of B equals prefix, B, prefix, A1. Segment tree, range sum and range update variance, both O, log n, per op. When to pick, if keys are indexed positions, time buckets, user id intervals. Bit is simpler and memory light. For arbitrary intervals with custom merge, use segment tree. Follow up. Shard by user underscore it or time underscore window. Each shard maintains its own segment tree. For range queries, query all relevant shards plus aggregate results. Use vector clocks for partial ordering of updates. Batch updates plus periodic sync between shards. Question 3. You are tasked with designing an ML model cache. Explain how a splay tree helps optimize access patterns, and what the trade-offs are compared to L or U caches. Follow up. When would splaying harm latency and serving predictions? Answer. An ML model cache needs to handle frequently accessed models efficiently. Splay trees are self-adjusting binary search trees that move recently accessed items closer to the root through splaying operations. How splay trees work? Basic concept. Every time you access a node, model, it gets moved to the root via tree rotations. Frequently accessed models naturally migrate toward the top. Less frequent models sink to deeper levels. Splaying operation. When you access a model, perform zig-zag or zigzag rotations to bring it to root. Time complexity, O, log n, amortized. Recently accessed models equals O, 1, access on next request. Question 4. Build a system to support efficient merging and karning of connected user components in a social graph. As edges are added or deleted for clustering and ML. Follow up. How does union by rank and path compression speed up large-scale ML graph operations? ANS. Building the system for connected components. To tackle this problem, a really effective and elegant approach is to use a data structure called the disjoint set union, DSU, or often just union find. Think of it as a specialized tool designed perfectly for keeping track of which group or component each user belongs to. Here's how we would build the system with it. Initially, we start by placing every single user in their own separate group. When a new friendship is formed, an edge is added between two users, we simply tell the system to unite their groups into one. If they were already in the same group, nothing changes. To check if two users are connected in the social graph, we just ask the system to find which group each user belongs to. If they are in the same one, we know there's a path between them. The beauty of this method is that adding new connections and checking for connectivity are both incredibly fast, while handling deleted friendships is a bit more complex, often requiring a periodic rebuild of the components. This union find approach is a wonderfully efficient foundation for clustering tasks and machine learning. Follow up. The power of union by rank and path compression. Now, what makes this union find method truly special for massive graphs are two clever optimizations: union by rank and path compression. Union by rank. This is a simple but powerful rule for merging. When we unite two groups, we always attach the smaller group to the larger one. This helps keep the structure of our groups flat and prevents them from becoming long, messy chains that would be slow to search through. It's a bit like a smart organizational chart that stays efficient. Path compression. This is another smart trick. Whenever we look up a user's main group, a find operation, we take a moment to update the connections for every user we passed along the way, making them all point directly to the top-level representative. The next time we look up any of those users, will find their group almost instantly. Together, these two improvements make the process astonishingly fast. Even with millions of users and connections, finding or merging components happens in what feels like a single step. This is what makes the union find data structure so powerful for large-scale machine learning, as it handles the massive scale of modern social graphs with ease.